Absolutely incredible. Elon Musk has just unleashed a whirlwind of updates regarding various facets of the Starship project, from launching and catching towers to upcoming missions and production plans. The excitement is palpable as we delve into the latest developments on today's episode of Great SpaceX. First up, let's talk about the launch tower. In the last days of 2023 and early 2024, SpaceX's launch tower segment delivery activities attracted a lot of attention. Over the past few days, SpaceX has also conducted activities with OLM at LC-39A. They also have plans to expand Starbase and take over the launch pad in Florida.
We're going to build more Mechazillas. So there's going to be 2 launch towers here, and then 2 launch towers at the Cape as well.
That is incredible news. That means that SpaceX is expanding its launch infrastructure with 2 launch towers at Starbase and 2 more at Cape Canaveral, bringing the total to an impressive 4 launch towers in the near future. The existing launch tower at Starbase was completed in 2021, and another one at LC-39A is nearing completion, marking significant progress in SpaceX's ambitious plans. And each region will soon welcome a new launch tower. At Starbase, SpaceX is asking the U.S. Army Corps of Engineers for 0.16 acres of wetland to build a second launch tower. Even if this is not approved, they still have many other areas like the suborbital test stand area to build a new launch tower. In Florida, SpaceX is also asking to take over LC-37 from ULA to build the Starship after the Delta IV Heavy retires. Secondly, Musk also revealed details about the construction time of these launch towers.
So we'll have 4 launch towers for Starship, probably by sometime next year. So we're aiming to have the first Cape launch tower and launch system operational around the middle of next year.
If what Musk said is true, we can expect new launch towers to be built in the next few months. With the first 2 launch towers, SpaceX still took about a year to complete. But with this experience, they may be able to shorten the construction time, but I estimate it could take still around half a year. Following construction, there will be a period of testing, likely lasting a few more months. Therefore, initiating the construction of a new launch tower soon, possibly as early as next month, will be crucial to meet the operational goal of mid-2025. Additionally, SpaceX will likely implement improvements to the launch system, particularly at LC-39 during this process. Once completed, the launch towers will undertake many important tasks like testing, launch, and catch. Also, in the recent company talk, Musk said SpaceX will land booster with a virtual tower in Flight 4 and land with Mechazilla arm in Flight 5. Musk confirmed this will be an 80 to 90% chance of success. But what does that actually mean? Well, we can expect to witness B-11 landing with a new method right in Flight 4 that may take place next month. A big step forward this will be for SpaceX's recovery stage efforts after the regrettable failure with B-10 in Flight 3. As for the ship, Musk said they need to have 2 consecutive successful landings, which means they still will try to splash down for about 2 more flights before returning it to the launch site. He also hopes to land Starship using a virtual tower somewhere in the Pacific or Indian Ocean similar to Booster in order to test the flip maneuver and vertical landing process. Musk's recent statements further reinforce the goals set by him and Gwynne Shotwell regarding the recovery of both stages this year, beginning with Flight 4 scheduled for May. In addition to launch towers situated on land, Musk showed images of an offshore launch tower system.
And then long term, we'll probably have some offshore launch sites.
This will further strengthen Starship's launch and catching system, as well as support another plan for the SpaceX Starship, Earth-to-Earth or point-to-point space travel. Thirdly, following updates on the launch tower and flight missions, SpaceX also revealed its prototype production plans. Specifically, they are aiming to build 6 pairs of boosters and ships. This progress will increase further next year with the participation of the Star Factory. After the revelations about the last version 1 prototype, the next 6 prototypes may be the first of the version 2. This is even more certain when the first rings, believed to be of the version 2, had appeared at Starbase. Also related to Starship versions, Musk also revealed many things about version 2 and 3 in this talk. Specifically, the current version is 121.4 meters high, but it will increase to 124.4 in version 2, and by version version 3 Starship will be at an astonishing height of 150 meters. With this improvement, version 2 will hold 3,650 tons of fuel in the booster and 1,500 tons in the ship, larger than the 3,300 tons in booster and 1,200 tons in Starship's version 1 iteration. But by version 3, this capacity will increase to 4,050 tons in the booster and 2,300 tons in the ship. Regarding the number of engines, the version 2 will still maintain 3 sea-level engines and 3 vacuum engines for the ship, much like the version 1. But by version 3, the ship will have 6 engines with 3 additional vacuum. Musk's recent revelations about the advancements in SpaceX's Raptor engine technology are truly mind-blowing. The progression from Raptor 1 to the anticipated Raptor 4, with its staggering thrust capabilities, showcases SpaceX's commitment to pushing the boundaries of propulsion systems. The thrust figures speak volumes. From 185 tons at sea level for Raptor 1 to an impressive 330 tons for Raptor 4, these engines represent a significant leap in power and efficiency. Furthermore, the simplicity and efficiency of Raptor 3, coupled with its omission of a heat shield, hint at its potential application in upcoming Starship versions. This streamlined design not only enhances performance but also reflects SpaceX's drive towards innovation and optimization. When we consider the total thrust of Starship in its various versions, such as the exponential increase from version 1 to 3, it's evident that SpaceX is gearing up for monumental achievements in space exploration. The plans for additional launch towers, upcoming flights like Flight 4 and Flight 5, and the unveiling of new Starship versions underscore SpaceX's ambitious goals and unwavering dedication to advancing humanity's presence in space. Overall, these revelations mark an exciting chapter in the journey towards interplanetary travel and colonization. As SpaceX continues to push the envelope of technology and exploration, the possibilities for the future of spaceflight are truly limitless. In late March and early April, crucial testing activities involving Flight 4 hardware were intensively escalated. The S-29 underwent 2 static fire tests on March 25th and 27th, followed by the B-11 completing a similar test on the 5th of April. Following these tests, the S-29 was rolled back to the high bay. Shortly thereafter, noticeable changes were observed as the heat shields in the nose cone were removed. Recent images from What About It depict the installation of new heat shields in this section. Moreover, on the 4th, during the transition of S-29 to make room for the S-30 prototype, it became apparent that many areas on the hull of S-29 no longer featured heat shields. Even the attachment pins were removed. This suggests a comprehensive effort by SpaceX to enhance details related to the heat shield, a component that encountered significant challenges during Flight 3. This focus is crucial considering that the primary objective of Flight 4 with S-29 will involve re-entry and splashdown. Musk recently articulated the goal for Flight 4 as get through high heating regime and smash into the ocean at a controlled spot, underscoring the importance of addressing heat shield concerns. Following an impressive static fire test, the B-11 was rolled to the Mega Bay on the evening of the 7th as anticipated. This move was expected due to the B-11 being initially transported to the launch site for testing without a crucial component, the hot staging ring. The return of the B-11 to the Mega Bay is likely to facilitate the installation of this essential system. Speaking of hot staging, the absence of this component accompanying the B-11 to the launch site may indicate that SpaceX has implemented significant upgrades to it. So, what are these upgrades? In a recent presentation by Musk, a new hot staging design was unveiled, reminiscent of the hot staging utilized on Russia's N-1N Soyuz rockets. This redesigned system is anticipated to be lighter and simpler than the current design, featuring larger vents to effectively direct and release heat and pressure sources. It remains uncertain whether the hot staging system on the B-11 adheres to this new design, as it has not undergone alterations in the Griffin like the proposed design. Therefore, we eagerly await further updates from SpaceX for clarification. In addition to the hot staging installation, the return of the B-11 to the Mega Bay provides SpaceX with the opportunity to inspect other critical systems such as the Griffin and engine. Following the impressive static fire test, engine testing becomes imperative to ensure reliability for the upcoming wet dress rehearsal test and the subsequent official flight. The Griffin is also a vital component that requires scrutiny, particularly considering SpaceX's intention to utilize a virtual tower system for booster landing. Both the Griffin and engine will significantly influence the success of this landing. As mentioned, with just over half a month remaining until May, SpaceX faces a tight timeline to complete work on S-29 and B-11. Subsequently, they must be rolled back to the launch pad for full stacking and the final crucial test, the wet dress rehearsal. If all progresses as planned, I anticipate that around the third week of this month, the Flight 4 hardware will be fully stacked and undergo testing. What are your thoughts? Feel free to let me know in the comment section down below. Now, let's shift our focus to the recent update from the Federal Aviation Administration, or the FAA, which holds significant importance in granting launch permits for Starship flights. In light of the estimates by the SpaceX leaders regarding the Starship launch in May, FAA officials have also issued noteworthy statements. Kelvin Coleman, FAA Associate Administrator for Commercial Space Transportation, remarked, "I think we can possibly get there. I'm not going to say we will get there absolutely in May, but I won't say it's out of the question either." Furthermore, Coleman emphasized that the Flight 4 launch license will require modifications due to the anticipated changes in flight profile, particularly the landing plan utilizing a virtual tower as recently revealed by Elon Musk. Additionally, the agency is striving to finalize public safety assessments of Flight 3 before granting licensing approval to SpaceX. In addition to the progress on licensing, the Federal Aviation Administration has delivered positive news to SpaceX. Recently, there were reports that the Biden administration was considering imposing taxes on commercial launch companies, notably SpaceX. This tax model resembled the policy currently applied by the Department of Transportation to commercial transport aircraft. The proposed tax aimed to support infrastructure development and address the impact of rocket launches on airspace. Previously, rocket companies enjoyed a tax-free ride regime. However, at the 39th Space Symposium on April 10th, Kelvin Coleman stated that the government currently has no plans to impose taxes on commercial launches. Specifically, he mentioned the president's budget request does not include a tax proposal. Coleman acknowledged that discussions about such plans had taken place, but clarified that they had not yet materialized into an official proposal. He concluded by stating, "At this point, there is no concrete proposal in the president's budget request. There are conservations, there's things we talked about, but I think there's still a way to go before we see something concrete in that regard." Certainly, the recent announcement brings relief to commercial launch companies, including SpaceX, following concerns over the proposed tax policy. Currently, SpaceX maintains its position as the world's leading rocket launch organization. In the previous year, they executed 98 rocket launches, representing nearly 80% of the total payload into orbit. For the ongoing year, SpaceX has ambitious plans to conduct up to 148 missions, with Elon Musk recently expressing the company's intent to boost the orbital launch rate to 90%. With this reassuring update, SpaceX can proceed with greater confidence in its plan. April saw significant attention drawn to the preparations for Starship Flight 4 in Texas, but that doesn't overshadow the remarkable achievements of other SpaceX systems. Recently, the reliable workhorse Falcon 9 once again made waves in the aerospace industry. On March 12th at 9:40 p.m. EDT, SpaceX launched the next Falcon 9 rocket, marking a crucial step in their 2024 plans. The mission took off from the SLC-40 launch pad at Cape Canaveral Space Force Station, Florida, carrying 23 Starlink satellites into orbit. Approximately 8.5 minutes after liftoff, the booster B-1062 successfully landed on the drone ship, a short fall of gravitas. The second stage continued its journey, flawlessly deploying the satellites into their intended orbit. With this mission, SpaceX completed its 38th Falcon 9 launch of the year, edging closer to the ambitious goal of 148 launches set for 2024. What sets this mission apart is its groundbreaking achievement in reusability, marking an unprecedented milestone in aerospace history. SpaceX has now achieved an incredible 20 successful launches, landings, and booster recoveries with the Falcon 9. That's right, 20 missions with a single booster. This milestone propels B-1062 ahead of other boosters like B-1060, 61, and 58, each with 19 launches, making it the booster with the highest number of reuse times in the Falcon 9 system. In fact, it now holds the distinction of being the most reused reused rocket component in the world. Following this mission, Elon Musk reposted SpaceX's tweet with the poignant message, "20th time the same booster has landed." This highlights the remarkable achievement of the Falcon 9 booster's unprecedented reusability. In a noteworthy exchange from 2020, ULA CEO Tory Bruno asserted that an organization must complete 10 flights to achieve a consistent break-even point, adding that no one had come close to achieving this. Elon Musk responded, revealing the initial challenges he faced in persuading his team about the viability of reuse, particularly through propulsive landing. This candid exchange underscores the visionary foresight and determination required to revolutionize the aerospace industry. This marks a significant stride for SpaceX in solidifying their position as a leader in reusability strategies. It's worth recalling the milestone achieved on December 23rd last year when B-1058, adorned with the iconic NASA logo, completed its 19th launch, a moment we'll always cherish. Unfortunately, that mission also marked the end of B-1058's journey, as it sustained damage during transport on the drone ship due to adverse weather conditions. However, the torch of increasing reusability has been passed on to other boosters, with B-1062 being the first to carry on the legacy initiated by B-1058. SpaceX promptly addressed the incident and reaffirmed their commitment to preventing its recurrence. True to their word, B-1062 encountered no issues during its 20th landing, underscoring the impeccable reliability of SpaceX's workhorse rocket. Following its return, the booster will undergo refurbishment and stand ready for its next mission. During its last flight, B-1062 achieved an impressive turnaround time of 28 days, significantly faster than its average frequency. This leaves us eagerly anticipating the next milestone this booster will achieve in the coming months. SpaceX has reached a significant milestone, halfway through their goal of achieving 40 flights for each booster. With 1062 leading the charge, SpaceX now boasts B-1060 and 61, each having completed 19 launches. Additionally, numerous other boosters are steadily advancing in their reusability efforts. Following this flight, SpaceX highlighted several additional noteworthy records achieved by B-1062. Since its inaugural launch in November of 2020, this booster has played a pivotal role in carrying out 8 astronaut missions and deploying over 500 satellites into orbit, totaling more than 261 metric tons in under 4 years. B-1062's impressive resume includes notable missions such as GPS-3 Space Vehicle 4, GPS-3 Space Vehicle 5, Inspiration 4, Axiom 1, Niosat 301, OneWeb Launch 17, Arabsat BADR-8, and now 13 Starlink missions. In addition to the remarkable progress made by booster B-1062, the SLC-40 launch system has also set new records. Notably, this launch system achieved its fastest turnaround to date, with a mere 2 days and 20 hours between launches. The most recent flight took place at 12:40 a.m. on the 10th of April. This achievement surpasses the previous record of 3 days and 17 hours set at the end of February. SLC-40's impressive turnaround time now exceeds that of the other two systems, SLC-39A and SLC-4E, which recorded 6 days and 18 hours and 5 days and 5 hours, respectively. The robust performance of SLC-40 underscores its significant contribution to SpaceX's operations. This year, SpaceX has implemented numerous upgrades to this launch pad, including the installation of a crew access arm and an emergency escape system. These enhancements are poised to bolster launch frequency, aligning with SpaceX's ambitious goals for this year and beyond. Moreover, SLC-40 will play a more prominent role in crew missions, complementing LC-39A, where the Starship system is located. With a third of the year already behind us, I anticipate SLC-40 will continue to operate with increased efficiency and productivity for the remainder of 2024, potentially setting even more new records. Free poses the most significant challenge for SpaceX at present. It might sound surprising considering their successful re-entry of spacecraft in the past few years. However, those accomplishments were with vehicles like Dragon, not Starship, the colossal behemoth currently reigning in space. Re-entering Starship is an entirely different ballgame compared to their previous endeavors with Dragon. The difficulties became apparent after their unsuccessful attempt with S-28 on Flight 3. Now, as Flight 4 approaches, it's crucial to delve into the monumental challenge awaiting Elon Musk and his team, successfully re-entering the world's largest rocket, Starship. Starship's operational horizons have expanded significantly since Flight 3. Following a remarkable liftoff, it embarked on several crucial missions at orbital altitude. The eagerly anticipated phase of re-entry and landing followed suit, pursuit. However, SpaceX's initial attempt during Flight 3 didn't result in an immediate triumph. Hence, Elon Musk has once again underscored the importance of the re-entry mission in the upcoming flight.
With Flight 4, we should, if we get, if fate smiles upon us, we'll get through the high heating regime and smash into the ocean at a controlled spot.
He added,
So the ship, I think we will want to have at least 2 consecutive successes of a given design that land at a specific point in the ocean or smash into a specific point of the ocean before we try to bring it back to the launch site.
Everything sounds promising, but before reaching that pinnacle, Starship must overcome the formidable challenge of re-entry, a task that has proven to be quite demanding for the spacecraft thus far. As we're all aware, our Earth boasts a dense atmosphere, a protective shield that sustains life and shields us from external threats. However, it's also this very atmosphere that poses a significant hurdle for spacecraft traveling to and returning from space. Typically during re-entry, a spacecraft is subjected to extreme temperatures reaching up to 2700 degrees Fahrenheit or 1500 degrees Celsius. Materials commonly used in spacecraft construction, such as steel, carbon fiber, and stainless steel, cannot withstand such harsh conditions. Therefore, for a vehicle to safely return to Earth, it must rely on 2 crucial elements, a heat shield and an engine. SpaceX's Starship is no exception to this rule. However, this presents a significant challenge for SpaceX in its upcoming flight. The 2 most critical systems for re-entry, the heat shield and the Raptor engine, are also considered the most complex systems on Starship. Let's go ahead and walk through the intricacies of the heat shield first. Heat shields are composed of tiles crafted from various mixtures. For instance, the Space Shuttle utilized a heat shield made from a carbon composite, while SpaceX's Dragon relies on a heat shield crafted from a phenolic impregnated carbon ablator, or PKX. In the case of Starship, its heat shield is constructed from ceramics combined with numerous other mixtures. Generally, these heat shields boast excellent heat resistance and serve to safeguard vehicles as they traverse the atmosphere. Setting itself apart from other spacecraft, SpaceX has implemented a hexagonal structure for the heat shield on Starship. Musk champions this design, believing it offers no straight path for hot gas to accelerate through the gaps. Given Starship's immense size, it's equipped with up to 18,000 tiles covering more than half of the ship prototype. These heat shields are affixed to the ship via a system of 3 pins. However, SpaceX has yet to achieve absolute reliability with this system. In Flight 1, a significant portion of the heat shield detached shortly after liftoff. Even after improvements in Flight 2, significant detachment still occurred in Flight 3. During the re-entry process, when the heat shield is crucial, many areas on S-29 were observed to lack tiles. While it performed adequately against the intense heat and formidable plasma encountered during re-entry, it may not be sufficient to overcome Earth's protective barrier. And after the failed re-entry attempt, I think people are very interested in the attachment issue between tiles and pins. Many hypotheses for this problem have been made. Firstly, perhaps not all the tiles were installed properly. For example, they were too loose to connect firmly to the pins. This also comes from a large number of heat shields, up to 18,000, making the checking process quite difficult. The second hypothesis related to the impacts of strong vibrations during liftoff and flight. It caused the connections between pins and tiles to become weak, leading to the falling of the tiles. We can see this on S-29 when some locations lost heat shields after its last static fire. Besides vibration, temperature effects like extreme cold from fuel and venting, or high temperatures from flight and re-entry may also reduce attachment ability. Whatever the reason, it's clear that it still cannot guarantee Starship's reliability to pass the re-entry process. They still need upgrades to the system, typically the removal of heat shields on S-29's nose cone recently. But that's just a small change. They will need to research and improve both tiles and pins to create a stable attachment throughout the mission. At the same time, increasing the heat shield limit is also important work. Despite the impressive performance in Flight 3, everything only lasted 4 minutes. So, can the heat shield still maintain that if there are no problems with the S-28? That being said, I think SpaceX still needs to find ways to improve heat shield capabilities in future prototypes, including the S-29. Next, let's delve into the second critical component, the engine. In addition to the heat shield, the ship's engines must operate with absolute stability during re-entry. While recent flights have seen issues primarily with the Super Heavy's Raptor engines, there haven't been reported problems with the ship's engines. However, in my view, there's room for improvement. For instance, on the last flight, SpaceX planned to relight the engine in space, but later canceled this mission. Whether this decision was due to engine issues remains unclear. Although the ship will splash down rather than perform a vertical landing, the engine's stability remains vital. It needs to function reliably to slow down and cooperate with the engine flap system to adjust the ship's re-entry posture. This underscores the need for SpaceX to fine-tune the ship's Raptor engines to ensure stable re-entry. First and foremost, the engine must perform flawlessly to propel the ship into orbit. Additionally, it must contribute effectively to the re-entry process. However, the Raptor engine hasn't yet reached the pinnacle of reliability as evidenced by the last-minute engine problems on the B-10 despite its prior stellar performance. This could be attributed to the engine undergoing multiple shutdowns and reignitions, a scenario that might repeat with S-29. To guarantee engine reliability, SpaceX must conduct extensive testing and inspection. The 2 static fire tests conducted at the end of March positive results. Subsequently, S-29 was relocated to the build site with notable activity including heat shield replacement. However, it's expected that the engine will undergo thorough testing before being integrated with the B-11 for the wet dress rehearsal and subsequent flight. I firmly believe that SpaceX is more than capable of overcoming these challenges, and they stand as the singular organization globally with the prowess to do so. Their track record speaks volumes. SpaceX has executed numerous re-entry maneuvers with the Dragon spacecraft over the years, including crewed flights, boasting an outstanding success rate. While Dragon is significantly smaller than the colossal Starship, SpaceX can leverage its wealth of experience to navigate this mission successfully. Moreover, SpaceX has achieved remarkable milestones with the landing of hundreds of Falcon rocket boosters, setting unprecedented records for reusability. While booster landing may differ from re-entry from orbit, the process of landing the ship post-re-entry shares similarities with booster landings. For the upcoming flight, the landing will occur over the ocean, with subsequent flights possibly utilizing the Mechazilla arm. In preparation for the next flight, SpaceX has made significant adjustments, such as replacing the heat shield in the nose cone, as previously mentioned. I'm confident that SpaceX has implemented numerous upgrades following the lessons learned from Flight 3. With time still available before the estimated launch schedule in May, SpaceX has ample opportunity to further enhance the prototype and ensure its readiness for the upcoming mission. There's no denying that SpaceX has a substantial amount of work ahead to ensure a successful re-entry in the upcoming flight. Re-entry for the ship will undoubtedly be the most formidable task Elon Musk and his team have faced thus far. From upgrading the heat shield to fine-tuning the engines, numerous elements must be enhanced to accomplish this critical endeavor. The outcome of the re-entry in this flight will significantly influence SpaceX's plans and the trajectory of the Starship project, yet it's often the toughest challenges that yield the greatest triumphs. Nearly a decade ago, SpaceX shattered conventional wisdom by achieving the seemingly impossible feat of vertical booster landing. Now they stand poised to astound the world once more with the successful re-entry of Starship. This momentous event could very well become a new symbol of innovation and advancement in the aerospace industry. So let's prepare to witness history in the making, possibly as soon as Flight 4. Get ready for a moment that could redefine our understanding of space exploration. It's fascinating to observe the similarities between pairs of ship prototypes upon closer inspection. Indeed, prototypes such as S-24 in Flight 1 share resemblances with S-25 in Flight 2, and similarly, S-29 slated for Flight 4 bears similarities to S-28 from Flight 3. This correlation may stem from these pairs being produced during the same time frame. However, the similarity in design doesn't imply a lack of changes for the hardware in Flight 4. On the contrary, upgrades have been implemented more robustly following Flight 3. Despite significant progress made during this flight, unfortunate incidents led to its partial success. Let's delve into the upgrades for B-11 first. We'll observe a notable change at the top of the booster, particularly with the Griffin. SpaceX has introduced some doublers beneath the Griffin's socket, along with 2 small reinforcement details above the socket. Additionally, there's been a redesign of the vent hole along with the surrounding welded steel plate. Previously, we noticed a prominent welded design featuring an H-shaped steel plate around the vent hole. However, the latest iteration showcases only 2 small steel plates positioned above and below the vent hole. Moreover, the weld for these steel panels has been notably reduced, resulting in a more aesthetically pleasing appearance. Interestingly, the vent itself appears to be smaller than its predecessor, though the reason for this change remains unclear. Regarding the upgrade of the steel plate, it's plausible that this adjustment aims to reduce the material required for this component and streamline the installation process. Looking beneath, specifically at the methane tank section, there's been a significant increase in the number of internal stringers, now totaling about 74 columns compared to the 24 in B10. This enhancement is straightforward to grasp, as additional stringers enhance the vehicle's durability when the booster releases fuel pressure. On top of that, it ensures the safety of the internal fuel tank against external impacts during testing or flight. Beneath the methane tank, notable changes are also observed in the liquid oxygen tank. B11 features numerous large doublers on the internal stringers, a feature absent in both B10 and previous prototypes. This adjustment mirrors the upgrade seen in the methane tank, serving to bolster the safety of the fuel within. Additionally, B11 has recently been transported to the launch site, revealing another intriguing observation: the absence of the hot staging ring on the top of the booster. Although there are no specific images available at present, it's possible that SpaceX is also upgrading this crucial system. These are just the initial alterations observed on the S29 and B11 prototypes. In the upcoming period, I anticipate numerous additional updates to be unveiled. If you come across any significant modifications to the Flight 4 hardware, feel free to share them in the comments section for further discussion. Next, let's get into the details of the modifications made for the S29. Indeed, it seems that SpaceX is making significant changes to the heat shield system on the nose cone of the S29 prototype. The removal of the heat shield tiles indicates a shift in the design approach. Previously, the nose cone had tiles with several seams, but it appears that SpaceX aims to eliminate these seams in the new version. This modification not only enhances the aesthetics of the nose cone, but also contributes to improving its reliability. As the first part of the rocket to encounter the environment during ascent and re-entry, ensuring seamlessness in the heat shield system is crucial for the overall performance and safety of the vehicle. It appears that SpaceX is implementing changes not only to the nose cone, but also to the heat shield system in other areas of the hull, particularly in the liquid oxygen tank and the aft flaps. In the S29 prototype, these parts featured horizontal seams in the heat shield system. However, in the S29 prototype, SpaceX is removing these seams to enhance seamlessness. This involves adjusting the layout of the heat shield, with the tiles adjacent to the seams being smaller than those in the same position on the S28 prototype. These alterations aim to improve the overall reliability and performance of the heat shield system during the spacecraft's ascent and re-entry. The upgrades implemented in the heat shield system, particularly the focus on consistency and seamlessness, are crucial for addressing the issues encountered during Flight 3. The re-entry phase poses significant challenges, with temperatures reaching up to 1500 degrees Celsius or 2700 degrees Fahrenheit. Any flaws in the heat shield could lead to catastrophic consequences for the spacecraft. By reducing disruptive details and ensuring a more uniform heat shield, SpaceX aims to enhance the stability and success rate of the re-entry process. While there were multiple issues affecting S28 during the previous flight, the upgrades to the heat shield system in the S28 are expected to be a significant factor in improving performance and ensuring a successful outcome for the upcoming flight. The upgrades to the Griffin system on the booster are crucial for ensuring smoother navigation and successful deceleration, especially following the issues encountered during B10's failure to decelerate as planned. These enhancements will contribute to improved functionality, helping the booster effectively navigate its remaining journey during the flight. Additionally, the increase in stringer and doubler components enhances the durability of the prototype, particularly in critical areas like the fuel tank, where essential processes such as venting occur. These upgrades will enhance the durability of the internal fuel system, mitigating the risk of incidents such as fuel leaks caused by external factors. And did you realize most of the aforementioned upgrades focus heavily on the landing process, something they did not complete in the previous flight? In Flight 3, S28 began re-entry around T plus 45 minutes, experiencing an impressive 4-minute re-entry phase. However, at approximately T plus 49 minutes, the signal was lost, seemingly indicating the end of its journey at the time. As for the booster, it was less than 500 meters from the ocean surface when it ultimately exploded. These events underscore the significance of re-entry and landing for SpaceX in the upcoming flight. Gwynne Shotwell revealed that Flight 4 will not carry a payload, allowing SpaceX to prioritize and refine these critical processes further. So, why are re-entry and landing so crucial? Well, SpaceX's mission has always been to revolutionize space travel by reusing rockets, a feat they've partially achieved with the Falcon 9. However, their ultimate aim is to take take this concept to new heights with Starship, achieving full reusability. This ambitious goal promises substantial savings in production and operating costs, allowing them to allocate resources towards pioneering efforts in reaching and establishing settlements on Mars. Moreover, the ability to fully reuse rockets will significantly slash launch costs and boost launch frequency. This competitive edge is pivotal in the ongoing space race, positioning SpaceX ahead of other rocket systems in the quest for space exploration dominance. In the upcoming flights, SpaceX will continue to land in the ocean. However, their future plans involve landing with the Mechazilla arm. Regardless of the method, all landings will hinge on a flawless re-entry, a skill SpaceX must master soon, beginning with Flight 4. Once this mission is accomplished, they can confidently escalate the challenge by incorporating the Mechazilla arm. Achieving a landing with the chopsticks would be a groundbreaking achievement, but when will this milestone be reached? It's likely contingent on the outcomes of the upcoming flights and the progress of constructing the new launch tower. Indeed, mastering re-entry and landing this year holds even greater significance as SpaceX approaches 2025, with a slew of crucial tasks on the horizon, such as developing a ship-to-ship refueling system and conducting uncrewed Starship HLS missions. To unlock these visions, Flight 4 stands as a pivotal moment, with landing taking center stage. Now more than ever, it's crucial for SpaceX to channel all its focus into perfecting this process. In just about a month's time, we'll have the opportunity to witness this pivotal flight firsthand. I'm eagerly anticipating SpaceX's unveiling of upgrades on the S-29 and B-11, and I'm particularly keen to see their effectiveness during flight. What are your thoughts on the new upgrades for Flight 4 hardware? Do you believe the next flight can achieve success with these enhancements? 3 integrated Starship flights have now taken place. Each of these flights has showcased the remarkable power generated by the Raptor engines, leaving observers like myself profoundly impressed. Yet the impact of the Raptor extends beyond its awe-inspiring thrust during flight. The engine's manufacturing process is also making unprecedented strides. With a production rate of 1 engine per day, the Raptor engine is revolutionizing traditional concepts of rocket engine production. However, this pace will soon become the new norm, albeit still relatively slow compared to the rapid pace of Starship's development. But just how remarkable is the frequency of the Raptor engine production, and how will this engine system be further advanced in the future? Join us as we delve into these questions on today's episode of Great SpaceX. While not yet officially operational, Starship is widely regarded as the most promising rocket in the world, potentially assuming the iconic role once held by the Saturn V or Space Shuttle. However, despite their shared status as giant rockets, Starship differs significantly from its legendary predecessors. One of the most notable distinctions lies in its engine configuration. Unlike the Saturn V or Space Shuttle, which utilized several large-sized engines, Starship employs numerous small-sized engines. We previously explored the rationale behind this design choice in a previous episode. If you'd like a more thorough understanding, feel free to revisit that discussion. This necessitates a significant requirement. SpaceX must produce a vast number of engines for its rockets. In the current configuration, Starship utilizes a total of 39 Raptor engines, comprising 33 engines in the Super Heavy booster and 6 in the Starship spacecraft. You may recall the image of NASA Deputy Administrator Pamela Melroy visiting the Starship factory a few months ago. At that time, SpaceX seemed to have achieved a milestone of producing 400 Raptor engines. Quite an impressive feat, isn't it? SpaceX anticipates conducting numerous flights in the future. Let's crunch some numbers focusing solely on the current prototypes at Starbase, ranging from S-29 and B-11 to S-32 and B-14. With 4 pairs of prototypes, SpaceX will require up to 156 engines, assuming the prototypes cannot be reused yet, representing nearly half of the engines they had just a few months ago. Despite reaching remarkable production milestones, this may not suffice to meet the demanding launch rates anticipated in the future. Moreover, it's important to consider that SpaceX plans to increase the number of engines for each Starship, further escalating the demand for engines. Elon Musk set a goal late last year to produce between 100 to 300 Starships annually. Achieving this objective would translate to the need for thousands of engines each year to power these ambitious spacefaring vessels. Undoubtedly, this presents a monumental challenge, one that may seem insurmountable for many organizations. Recognizing this potential scenario, SpaceX has been diligently increasing its engine production rate over the years. Between 2018 and 2021, SpaceX utilized the Raptor 1 version. During this period, they manufactured a total of 100 engines, equating to roughly 2 weeks for each engine. This relatively slow pace can be attributed to the fact that the Raptor engine system was still relatively new at the time. Furthermore, the design of the Raptor 1 engine is intricate, characterized by numerous small details. This complexity contributed to the comparatively sluggish production speed, although it still outpaced many other engine systems in the industry. Following that, SpaceX transitioned to producing the Raptor 2 version. In less than a year, SpaceX announced the production of 200 engines, indicating a significant improvement in efficiency. With this version, SpaceX streamlined the manufacturing process, resulting in an impressive production rate of approximately 2 days per engine, a remarkable advancement compared to the previous version. The enhancements made to the Raptor 2 not only simplified its design, but also increased its power, surpassing its predecessor. By the end of 2022, SpaceX had further accelerated its production speed, achieving a rate of 1 engine per day. Extrapolating from the progress made since Pamela Melroy's tweet over 5 months prior, SpaceX likely reached a production milestone of around 550 to 600 Raptor engines. Yet, whether SpaceX has produced 400 or 600 engines, it remains insufficient to meet the formidable demand they have set. To keep pace with their ambitious goals, SpaceX will need to accelerate production even further. Nonetheless, they possess a solid foundation to believe in achieving this new miracle. Firstly, SpaceX boasts extensive experience in engine production, as evidenced by their track record of developing engines over many years. This expertise extends beyond the Raptor engine to include the Merlin system used in the Falcon rockets. Moreover, SpaceX is committed to continuous improvement, evident in their testing of a new version, Raptor 3. This iteration is purportedly much simpler than Raptor 2, enabling SpaceX to ramp up production significantly. Secondly, SpaceX benefits from the impending operation of their new production facility, Star Factory. Construction progress on this facility has been accelerated following the demolition of old systems. Designed with an automated production model akin to Tesla's Gigafactory, Star Factory is poised to revolutionize production efficiency. SpaceX's ultimate goal is to manufacture 1 Starship per day. With this infrastructure in place, producing dozens or even hundreds of engines every day becomes a realistic possibility. Elon Musk recently underscored this capability in a tweet stating, "Compared to the insane pain of reaching high volume, positive margin production, prototypes are a piece of cake." This sentiment reaffirms SpaceX's confidence in their ability to achieve high-volume engine production. In addition to ramping up production, SpaceX must prioritize enhancing reliability in the foreseeable future. While each flight of the Raptor engines has shown progress, it's undeniable that challenges persist. In the maiden flight, booster engines were shut down shortly after liftoff, resulting in a premature end to the mission after just 4 minutes. In the second flight, the engines failed to reignite after separation, leading to the booster's inability to control its landing. The third flight appeared to proceed flawlessly until the booster engine encountered a last-minute issue, preventing successful deceleration and landing. Hence, alongside accelerating production, SpaceX must conduct meticulous testing before deploying engines into operation. Flight data analysis is ongoing and will inform upgrades to various components, including the engines. This iterative improvement process has been a consistent practice after each previous flight. Even after installation in the booster or spacecraft, engines undergo continuous testing, including spin prime, static fire, and wet dress rehearsal, in order to ensure their reliability and performance. On top of upgrading current engines, SpaceX is pursuing reliability enhancements through design changes in new engine versions, following a long-standing principle of simplification. Elon Musk's mantra, "the best part is no part," underscores this approach. Simplification not only enhances engine power, but also facilitates production, maintenance, and minimizes potential issues during flight, common occurrences with complex and vulnerable components. Regarding the release of Raptor 3, speculation abounds. Personal predictions vary, but I foresee Raptor 3 being introduced alongside the utilization of new Starship versions, such as version 2 or 3. These iterations are anticipated to be larger with significant increases in height. Consequently, overall mass, payload capacity, and fuel volume will also increase. To maintain or even enhance flight performance, SpaceX will require a more potent engine, making Raptor 3 the optimal choice for this evolution. As previously noted, SpaceX has 4 pairs of prototypes remaining for version 1, slated for flights from 4 to 7. Given SpaceX's target of 5 to 6 flights this year, these prototypes may soon be depleted. Therefore, it's reasonable to anticipate that next year will herald the introduction of the new version of Starship. This impending milestone suggests that Raptor 3 will soon enter production to align with the new hardware requirements. The advancements of the Raptor engine will play a pivotal role in the evolution of the Starship project. Coupled with the capabilities of Star Factory and the significant enhancements of Raptor 3, SpaceX's engine production rate is poised to surge even further. This acceleration will widen the gap between SpaceX's Raptor engines and those of competitors such as Blue Origin's BE-4, NASA's RS-25, or Russia's RD-180. Needless to say, the trajectory of the world's largest rocket, the Raptor, promises significant developments in the future. With its high production frequency, unparalleled thrust, and remarkable reliability, the Raptor engine is reshaping the entire landscape of the global rocket engine industry. As humanity sets increasingly ambitious goals in space exploration, the demand for greater thrust capabilities becomes imperative. SpaceX's team comprehends this necessity well, and their relentless pursuit of innovation ensures they maintain a leading position in the space race. Their ongoing development efforts are crucial in propelling humanity towards the next frontier of space exploration. Before delving into the updates regarding the latest iteration of the Raptor engine, let's once again marvel at the awe-inspiring power of the Raptor through this video. With 3 successful integrated flights of the Starship behind us, each yielding varying results, one constant factor remains. The colossal Starship rocket consistently exhibits mind-boggling thrust. And at the heart of these incredible thrusts are the powerful Raptor engines. Equipped with the Raptor 2 version, Starship boasts a liftoff thrust exceeding 7,000 tons, a force twice as potent as that of the Saturn V. But the advancements don't end there. Last May, SpaceX unveiled yet another iteration, the Raptor version 3, boasting an estimated thrust of up to 269 tons, or 593,000 pounds. This undoubtedly leaves any would-be challengers of the Raptor family feeling utterly disheartened. And just recently, Musk dealt another blow to his adversaries. Alongside the presentation of the 3 existing Raptor versions, he had yet another revelation.
I think ultimately the booster engines will aim to get the booster engines over 330 tons of thrust, which would mean 10,000 tons of total thrust at liftoff.
Indeed, a thrust of 330 tons or roughly 727,000 pounds is absolutely mind-blowing. This undoubtedly hints at a version previously unmentioned, possibly the newest edition of the Raptor family, the Raptor 4. This speculation arises because even the most powerful version to date, the Raptor 3, achieves a thrust of only 280 tons at sea level and 306 tons in vacuum. While this thrust surpasses the data disclosed from the May 2023 test, it falls short of the parameters outlined by Elon Musk. Musk's revelation has sparked numerous questions, particularly regarding how the engine's hardware can withstand such immense thrust and pressure. However, it appears Musk's statement was not made lightly. In a tweet on X, he declared, "Raptor operates close to the ragged edge of physics," indicating that SpaceX is capable of pushing the boundaries even further. This suggests that beyond Raptor 4, subsequent iterations like Raptor 5 and 6 may emerge with even more astonishing capabilities. Skipping ahead, let's explore the astounding capabilities of this engine with its current specifications through a few straightforward calculations and comparisons. With the booster, SpaceX intends to utilize 33 engines across all versions. Under this configuration, the liftoff thrust of the Super Heavy equipped with Raptor version 4 is expected to reach up to 10,890 tons, or around 24 million pounds. As for the ship, while Musk hasn't specified the thrust for the vacuum version, based on the historical ratio in previous versions, the Raptor vacuum typically exhibits about 20 tons more power than its sea-level counterpart. Hence, we can assume that the Raptor version 4 vacuum will achieve approximately 350 tons of thrust. With a 6-engine layout, the ship will boast a thrust of up to 2,040 tons, or 4.5 million pounds. Comparatively, the thrusts in both the booster and ship equipped with Raptor 4 will be 18% stronger than those of the Starship, utilizing Raptor 3 with 280 tons of thrust and a whopping 40% more powerful than the Starship, utilizing the current Raptor 2 version. Even with a configuration of 3 sea-level engines and 6 vacuum engines, the thrust would still soar to an impressive 3,090 tons or 6.8 million pounds. Truly formidable, isn't it? But it's not just about the thrust. Raptor 4 is anticipated to bring a plethora of remarkable updates in design. While the specifics of the Flight 4 design have yet to be unveiled, the comparison slide showcasing the 3 Raptor versions gives us a glimpse into what to expect. Raptor 3 boasts a unified structure, significantly simpler and tidier than its predecessor, Raptor 2. With only a handful of minor details remaining, Elon Musk mentioned that numerous intricate elements have been either concealed, eliminated, or amalgamated. The incorporation of integral cooling channels means Raptor 3 won't necessitate a separate heat shield. This streamlined design not only reduces mass, but also enhances the performance and reliability of the new engine. Building upon these advancements, Raptor 4 is poised to be even simpler, potentially eliminating any vulnerable systems. Many, including myself, are eagerly anticipating the unveiling of this incredible design and hope to see it materialize in the near future. Let's expand this comparison to include other engines in the industry. Firstly, let's juxtapose the Raptor 4 with another methane engine, the Blue Origin BE4. Prior to the unveiling of the new Raptor versions, the BE4 engine already boasted greater power than the Raptor 2 with a thrust of 250 tons or 550,000 pounds. However, upon its launch, Raptor 4 will surge ahead, delivering a thrust that is 32% higher than that of the BE4. It's worth noting that New Glen's or Vulcan's booster relies only on 7 and 2 BE4 engines respectively, meaning that the liftoff thrust of the Starship will be 6 times more powerful than that of New Glenn and nearly 22 times greater than that of the Vulcan. Now, let's substitute the BE4 with the RS-25, the engine utilized on NASA's Space Launch System, or SLS for short. In terms of standalone thrust, the RS-25 falls short, achieving only 223 tons or 492,000 pounds. This means that Raptor 4 will outperform the RS-25 by up to 47%. Moreover, the RS-25 is inherently less powerful than the current Raptor 2. When combined with solid-side boosters, the SLS exhibits a liftoff thrust of 8 million pounds, merely half of that of the current Starship. Thus, the introduction of Raptor 3 or 4 may further widen the disparity between SpaceX's rockets and NASA's. Now, let's delve into comparisons with the Russian RD-180 engine. Each RD-180 engine achieves a thrust of 390 tons or 860,000 pounds. Currently, each Soyuz rocket utilizes 20 engines in the core booster and 4 side boosters, resulting in a liftoff thrust of 7,800 tons or 17.2 million pounds, surpassing that of the Starship version powered by Raptor version 2. However, with the advent of Raptor version 3, Starship's total thrust officially surpassed that of the Soyuz, and this trend continued with the introduction of version 4. Based on the provided data, Starship's liftoff thrust with the Raptor version 4 will be nearly 40% stronger than that of the Soyuz. Finally, let's compare Raptor 4 with the industry standard, the F1 engine. This legendary engine still holds the record for the most powerful thrust, reaching up to 1,522 million pounds or 690 tons, twice as powerful as the version 4 of Raptor. However, considering that the Saturn V utilizes only 5 F1 engines, its thrust amounts to only 3,450 tons or 7.61 million pounds, merely half that of the current Starship version. If Raptor 4 were to be employed, Starship would be over 3 times more powerful than the thrust of the Saturn V. In addition to thrust comparisons, another significant parameter is the engine's chamber pressure. While Raptor 2 achieved a chamber pressure of 300 bar, testing in May suggests that Raptor version 3 may reach 330 bar. It's anticipated that Raptor 4 will surpass this, showcasing its superiority over the engines listed earlier. The BE4 reaches only 134 bar, the RS-25 at 206.4, and the RD-180 manages 257.5 bar, significantly lower compared to Raptor 2, 3, and the anticipated capabilities of the version 4. Now, let's explore the anticipated timeline for the appearance of Raptor 4. As of now, we haven't witnessed the introduction of the Raptor 3 version, suggesting that the release of Raptor 4 may still be quite distant. Even during the presentation presentation introducing the version 2 version, the total thrust didn't align with that of Raptor 4. Instead, Starship 2 still appears to utilize Raptor version 3. It's possible that we may have to wait until the unveiling of Starship version 3 to witness the debut of Raptor 4. Indeed, with the projected thrust of 10,000 tons in the booster of Starship version 3, only Raptor 4 would be capable of meeting such demands. So, when can we expect the production of Raptor version 3 and 4? As previously confirmed by Musk, S32 appears to be the final prototype of version 1, with booster designated as B14. In the presentation, Musk indicated that this year they would manufacture 6 more pairs of Super Heavy and ship prototypes, likely representing Starship version 2 and Raptor 3. Previously, SpaceX spent 4 years developing Raptor 1 before transitioning to Raptor 2. With Raptor 2 in use for over 2 years now, the possibility of Raptor 3's introduction looms on the horizon. However, SpaceX must meticulously evaluate the design and performance of Raptor 3 before determining whether to proceed with Raptor 4. This evaluation process typically involves 5 or 6 test flights. Given the current pace, could span nearly a year. With 4 version 1 prototypes still in SpaceX's possession, the earliest we might witness the liftoff of Starship version 2 is likely next year. Consequently, the debut of Raptor 4 and Starship version 3 may not occur until late 2025 or early 2026. But there's still a possibility that they could debut earlier, coinciding with the production and operation of Raptor 3 and Starship version 2. The introduction of Raptor 4 marks a paradigm shift in the rocket engine industry, surpassing all prior expectations. Its unparalleled power solidifies the dominance of the Raptor family and underscores SpaceX's relentless pursuit and pushing the boundaries of possibility as articulated by Elon Musk. Looking ahead, SpaceX is poised to continue pushing the limits with the potential development of Raptor 5, 6, and beyond. While the exact timeline for these advancements remains uncertain, one thing is clear: Raptor 4 rightfully earns the title of the new king of engines. Established in 2006 through the merger of Boeing and Lockheed Martin, ULA has been a formidable force in the aerospace industry. This merger brought together 2 powerhouse companies, each with its own renowned rocket family, Atlas and Delta. These rockets have played pivotal roles in numerous government and military programs, solidifying ULA's position in the U.S. aerospace sector. After over 17 years of development, ULA recently introduced its latest rocket, the Vulcan Centaur. This new addition is poised to bolster ULA's competitiveness in the face of stiff competition from rivals such as SpaceX and Blue Origin. Despite initial doubts, the debut flight of the Vulcan Centaur in January proved to be a success, showcasing ULA's continued innovation and commitment to advancing space exploration. Despite ULA's confidence in their systems and Tory Bruno's assertion that competition is beneficial for the industry and customers, Elon Musk's prediction about ULA's challenges appears to be materializing sooner than expected. While ULA's rocket families, including the newly launched Vulcan Centaur, may give the impression of strength and a promising future, the reality seems to be more complex. It's clear that ULA is facing significant obstacles and uncertainties in the current landscape of the aerospace industry. To illustrate this, let's rewind to March 28th at SLC-37, where the Delta IV Heavy rocket was scheduled to launch its final mission. Before the planned launch time of 2:03 Eastern, ULA indicated that all processes, including fueling, were proceeding smoothly, with no reported issues from the team. However, the liftoff time was delayed by nearly an hour, hinting at potential complications. Ultimately, the flight was scrubbed due to adverse weather conditions and an issue with the gaseous nitrogen pipeline, which provides pneumatic pressure to the launch vehicle systems. Although a new launch date was set for March 29th, the problem persisted and the launch schedule for the Delta IV Heavy was labeled as unknown. This sequence of events highlights the significant challenges faced in completing the final mission of the Delta IV Heavy rocket. The recent issue with the Delta IV Heavy mission serves as a microcosm of the broader challenges facing ULA over the years: technological stagnation and a dim outlook for the future. The signs indicating the potential demise of ULA have been apparent for some time, particularly when examining their rocket systems. Rockets such as the Atlas and Delta have gradually become outdated after decades of service, retaining characteristics of older generation rockets. For instance, the Atlas V still relies on the Russian generation RD-180 engine. While the introduction of the Vulcan rocket represents a step towards reducing their dependence, none of ULA's vehicles are reusable. This stands in stark contrast to competitors like SpaceX and Blue Origin, which have embraced reusability as a key strategy. The advent of reusable rockets has played a pivotal role in SpaceX's dominance of the orbital launch market for nearly a decade. Thus, while ULA may have made strides in modernizing its fleet with the Vulcan rocket, its failure to adopt reusability has left it at a significant disadvantage compared to its competitors. This, coupled with other challenges, suggests a challenging road ahead for ULA in an increasingly competitive space industry. Why don't we delve deeper into each of ULA's rockets, starting with the Vulcan Centaur, hailed as the future of ULA. While its impressive performance in January cannot be denied, it's crucial to recognize the extensive time and resources invested by ULA to achieve this milestone. Developed since 2014 and undergoing years of testing, the Vulcan was initially slated for a 2021 launch. However, issues with the BE-4 engine and the Centaur second stage led to delays, pushing the launch to early 2024. These setbacks have had significant economic repercussions for ULA, contributing to the decision to sell the company. Despite its potential for future development, the Vulcan faces stiff competition from rockets with established track records of success, such as SpaceX's Falcon 9 and Falcon Heavy. As for ULA's older generation rockets, the outlook appears bleak. The Delta IV Heavy, the last member of the Delta family, recently embarked on what was supposed to be its final mission. Despite its storied history, the retirement of the Delta IV Heavy marks the end of an era for ULA. Similarly, while the Atlas V has 17 missions scheduled until 2029, these are expected to be its last before retirement. With limited potential for further development, both the Delta IV Heavy and Atlas V face uncertain futures in an evolving space industry dominated by innovative and reusable rocket technologies. The decline in ULA's rocket systems has led to setbacks across various fronts, including their performance in launching government and military payloads, a market segment where Tory Bruno and ULA have historically taken pride. However, they are now facing increasing competition from SpaceX. A notable example is Phase 2 of the U.S. Space Force's National Security Space Launch Program, or NSSL for short. Despite an expansion of the total number of missions from 34 to 48, ULA's mission ratio decreased from 60 to 54%, while SpaceX's share increased from 40 to 46%. While these fluctuations may not appear significant at first glance, they underscore a broader trend: ULA's gradual erosion of dominance in a domain where they once held sway. The shifting landscape reflects SpaceX's rising prominence and success in challenging ULA's long-standing position in the government and military launch market. In stark contrast to ULA's decline, SpaceX is experiencing exponential growth at an astonishing rate. As many are aware, SpaceX boasts the most stable and reliable launch vehicle in Falcon 9. With a record-breaking 60 flights in 2022 and an impressive 91 in 2023, Falcon 9 has firmly established itself as the most launched vehicle in a single year. This record is poised to be shattered soon, however, as SpaceX aims for a staggering 148 launches this year. Despite launching fewer missions, Falcon Heavy still achieves remarkable success, with 5 launches completed last year. In terms of orbital payload, SpaceX reached a staggering 1,200 tons in 2023, surpassing all other players in the whole of the aerospace industry. SpaceX has emerged as the top choice for organizations worldwide, including NASA and the military, for critical missions. Moreover, SpaceX's orbital fleet recently welcomed a new addition, Starship. Despite encountering some setbacks, including a partially successful third mission on March 14th, SpaceX has made significant strides with Starship. This year, SpaceX plans to conduct 5 to 6 flights with Starship. Unlike ULA's rockets, Starship holds immense potential for pivotal endeavors such as lunar landings and Mars colonization. These capabilities position Starship as the leading vehicle in the aerospace industry's future. One notable advantage of SpaceX's vehicles is their reusability, a feature that sets them apart from both ULA's older and newer rockets. This capability not only allows SpaceX to significantly reduce costs, but also enables them to increase launch frequency and enhance competitiveness relative to all competitors in the industry. Now more than ever, ULA can only hope that the new owner has plans to revitalize their systems. Since ULA announced the company's sale, numerous organizations have expressed keen interest in this deal. Among Among them, Blue Origin, led by billionaire Jeff Bezos, stands out as the most likely candidate to acquire ULA. With his substantial economic resources, Jeff Bezos is well positioned to make such a move. The potential union between ULA and Blue Origin has generated considerable anticipation. These two entities have a history of collaboration, particularly evidenced by their partnership in the development of the BE-4 engine. Additionally, both ULA and Blue Origin serve as launch service providers for Amazon's Kuiper satellite, a venture founded by Bezos. Notably, both the Vulcan Centaur and New Glenn rockets utilize the BE-4 engine. Therefore, if Blue Origin were to acquire ULA, they would inherit a robust rocket lineup without the need to undertake engine design stages for the Vulcan. This acquisition could provide Blue Origin with a formidable pair of rockets to compete with their primary rival, SpaceX, which boasts a powerful orbital fleet including Falcon 9, Falcon Heavy, Dragon, and the promising Starship. However, despite the potential benefits of this combination, it may not be sufficient to surpass SpaceX. SpaceX's dominance in the industry is considerable, and bridging the gap between Blue Origin and SpaceX would be a formidable challenge. Nonetheless, such a move could help Blue Origin narrow the significant disparity that SpaceX has established over the years. The divergent trajectories of ULA and SpaceX underscore the prevailing dynamics within the aerospace industry. It's regrettable to witness the potential demise of a prominent entity like ULA. However, the harsh reality is that survival and long-term success in the industry necessitate continuous innovation and adaptation to the evolving landscape. Among all contenders, SpaceX excels in this regard, positioning itself at the pinnacle of the global aerospace industry. Specifically, the White House has tasked NASA with creating a new time zone for the moon by the end of 2026 as part of the United States' broader goal to establish international norms in space. The direction to set up a lunar time zone comes amid growing global interest for humanity to establish a long-term presence on the moon in the coming years, a chief priority of NASA's Artemis program. According to an April 2nd memo by the White House Office of Science and Technology Policy, the new lunar standard called Coordinated Lunar Time, or LTC, is part of a broader effort to establish time standards at and around celestial bodies other than Earth. It was not immediately clear whether the moon would have multiple time zones as Earth does. The memo also stated, U.S. leadership in defining a suitable standard, one that achieves the accuracy and resilience required for operating in the challenging lunar environment, will benefit all spacefaring nations. Steve Welby, the OSTP Deputy Director for National Security, said in a statement, as NASA, private companies, and space agencies around the world launch missions to the moon, Mars, and beyond, it's important that we establish celestial time standards for safety and accuracy. Because there is lower gravity on the moon than on Earth, time there moves slightly faster, about 58.7 microseconds faster every day. Though minuscule, that difference would make it harder for the growing number of future missions to communicate with each other, and for mission control to accurately track satellite and crew positions, among other issues. On Earth, time is measured by numerous atomic clocks placed in various locations around our planet. A similar ensemble of atomic clocks on the moon itself may be used for lunar timekeeping. In an interview with The Guardian, Kevin Coggins, a majestic name, manager of NASA's Space Communications and Navigation Program, said, an atomic clock on the moon will tick at a different rate than a clock on Earth. It makes sense that when you go to another body like the moon or Mars, that each one gets its own heartbeat. In space, there are a couple of different ways in which space agencies keep time. Astronauts aboard the International Space Station, which is in low Earth orbit, follow Coordinated Universal Time, or UTC. For spacecraft elsewhere, NASA uses spacecraft event time to catalog key mission events like science observations or engine burns. To establish LTC on the moon, the space agency told NPR that subject matter experts throughout the international community are discussing an approach to provide recommendations to the International Astronomical Union for a lunar reference frame and time systems. Regarding the schedule, the LTC will be established 3 months after Artemis 3, which may be launched no sooner than September of 2026. Moving on to an update from Rocket Lab, the company has unveiled its ambitious plans for rocket reuse. Currently, Rocket Lab is gearing up for its next launch, scheduled for no earlier than April 24th from Launch Complex 1 on the Mahia Peninsula in New Zealand. Dubbed Beginning of the Swarm, this mission will deploy 2 payloads to entirely different orbits. The primary payload for this mission is the NeonSat-1 satellite. This satellite is poised to assist the Korea Advanced Institute of Science and Technology and Satellite Technology Research Center in Earth observation. Equipped with a high-resolution camera, NeonSat-1 aims to facilitate monitoring of the Korean peninsula during natural disasters. Notably, this launch marks the commencement of an 11-satellite constellation for South Korea, with NeonSat-1 slated for deployment into a 520-kilometer circular Earth orbit. In addition to NeonSat-1, the Beginning of the Swarm mission will carry NASA's Advanced Composite Solar Sail System, or ACS-3, as its secondary payload. This CubeSat is designed to test new materials for deployable booms that will support a solar sail. Once fully deployed, the solar sail will measure approximately 30 feet per side. Following deployment by Rocket Lab's Curie kick stage, ACS-3 will enter a 1,000-kilometer circular Earth orbit. Following that, the kick stage will ignite once more to lower its orbit, facilitating a faster re-entry into the atmosphere and mitigating the risk of becoming space debris. Furthermore, an essential objective for Rocket Lab in this mission is the reuse of the first stage. Building on their previous efforts during the flight last January, Rocket Lab recently announced at the Space Symposium in Colorado that they have integrated a previously flown Electron first stage back into their production line. This marks a significant step forward in their ongoing pursuit of rocket reusability. The first stage tank has undergone rigorous testing, surpassing expectations by enduring leak checks, structural testing, and excess pressure for over 20 times the normal flight duration, paving the way for its reintroduction into the production line. This particular first stage played a pivotal role in the 4-of-a-kind mission on January 31st. Rocket Lab has not disclosed whether any of the Rutherford engines from that mission will be reused or if all new engines will be utilized. Furthermore, the company has yet to unveil which payload will be launched using the flight-proven first stage. Rocket Lab's progress toward achieving full first stage reusability on Electron signifies a significant milestone, accompanied by the accumulation of invaluable data that will inform their efforts to recover Neutron, their upcoming medium-lift rocket. Rocket Lab's continued emphasis on reusability underscores its impact on the rocket industry. While its scale may not rival that of larger entities like Blue Origin, ULA, or Russia, Rocket Lab is achieving feats that these industry giants have yet to accomplish. While it may not match SpaceX's mastery of reuse, with hundreds of successful landings and recoveries of Falcon first stages, Rocket Lab's progress positions them as a formidable contender in the race towards sustainable spaceflight. Their advancements pave the way for a promising future of development and innovation within the company. Turning our attention to the upcoming lunar mission known as the Griffin mission, following the Peregrine mission in January, Astrobotic is preparing to launch another rover to the moon. This time, the Pittsburgh-based company plans to deploy its Griffin moonlander atop a SpaceX Falcon Heavy rocket later this year. Griffin's primary objective is to deliver NASA's ice-hunting Viper rover to the lunar South Polar region, marking another significant step in lunar exploration. However, there is a possibility that the lander may also carry another small rover named Cube Rover. This modular rover is designed to democratize moon exploration, offering accessibility to a diverse range of customers. It will be controlled using Spacefarer, a software platform developed by the Canadian company Mission Control. During the press conference at the 39th Space Symposium, Lisa Campbell, president of the Canadian Space Agency, expressed her enthusiasm, stating, "What an exciting time in space exploration, as commercial companies are at the very beginning of creating a new market economy on the moon. This mission promises to be groundbreaking, a demonstration of commercial space technology, but quite frankly, I think it's just going to grow from here." The stationary lander's primary payload is Viper, or Volatiles Investigating Polar Exploration Rover. Astrobotic secured a $199.5 million contract from NASA's Commercial Lunar Payload Services program, otherwise known as CLPS, in June of 2020 to safely deliver Viper to the lunar surface. Mons Muon is situated near the lunar South Pole, an area believed to be abundant in water ice. This abundance of resources aligns with NASA's plans to establish a base on the region through its Artemis program. However, the actual quantity and accessibility of ice near the South Pole remain uncertain, and this is where Viper plays a crucial role. Viper, weighing approximately 1,000 pounds or 450 kilograms and comparable in size to a golf cart, will undertake a mission lasting about 100 Earth days. Its primary objective is to meticulously map out the distribution and concentration of water ice in the Mons Muon region. This data will be invaluable for future lunar exploration and potential utilization of lunar resources. NASA officials stated in a mission description, NASA will leverage the data collected by the rover to pinpoint the most promising locations for lunar ice and identify areas that are easily accessible. Viper will thus become the first ever resource mapping mission on another celestial body. These initial resource maps of the moon will represent a significant leap forward for NASA's Artemis missions aimed at establishing a sustained presence on the lunar surface. Meanwhile, the shoebox-sized Cube rover will undertake a demonstration mission supported by the Canadian Space Agency's CSA Lunar Exploration Accelerator program. This compact rover will be deployed after Viper, descending from the Griffin lander to the lunar surface via cables. Cube rover will conduct surface operations for 1 lunar day, equivalent to approximately 2 Earth weeks. During this time, it will undergo communications trials with the Griffin lander, traverse in the lander's shadow to assess its ability to withstand thermal extremes, and demonstrate the capabilities of the Spacefarer operating platform on the lunar surface for the first time, assuming all goes as planned. However, this inaugural mission represents just the beginning for Cube rover, according to Astrobotic. This versatile wheeled robot has the potential to be scaled up to accommodate larger payloads in the future. Subsequent versions could carry scientific instruments and other equipment across the lunar terrain, remaining operational for a year or more, as Mike Provenzano, Vice President of Advanced Development Programs at Astrobotic, explained. In addition to Viper and Cube rover, Astrobotic has disclosed several other payloads slated to fly on Griffin 1. These include the European Space Agency's LandCam X landing camera system and a NASA laser retro reflector. Further payloads may be announced in the forthcoming weeks and months, underscoring the breadth and significance of the mission. Well, folks, that's about it for today's episode. Thank you so much for tuning in, and as always, this has been Kevin from Great SpaceX, and until next time, keep looking up.